Boris, can you hear? Oh, he's
Yes,
here.
yes,
I can hear too.
yeah. Well, thanks for the 110 room. It's fantastic.
How about now, Boris? Can you hear?
Yes.
Should I hide? I should hide everything. Like that? Okay, it's me again, everybody. All right, so good. Let me I'll roughly continue from during the colloquium. So let's see. Okay. Great. One of the things we're interested in studying in our cold atom quantum simulators is the effect of as you know from your understanding of condensed matter physics, many materials, okay, so this is now a materials question. Many materials, when you cool them down to low temperature, they adopt some kind of ordered low energy phase. And that phase can often be disappointingly, maybe it's a ferromagnetic or something where you can write down, basically classically, you can write down a description of the state of the system. It's plenty interesting, of course, but maybe at some point you also want to study materials that kind of defy our this kind of simple description and might instead adopt a state of matter that is more complicated, more requiring of some fancy ideas for quantum. In order to find materials that fall into this more interesting, or sorry, different but quantum category of states rather than the more classical, one approach to doing this is to design a material so that there's nothing that favors a particular classical state. And if that occurs, then maybe there's very many classical states in energy. And now at low temperature, the system has to figure out some interesting superposition. And that's the interesting quantum. And one route to prohibiting a system from picking out one classical answer to its low energy ground state and being forced to examine many of them is this idea of geometric frustration. That there's something built into the connectivity of the system that prevents it from finding just one solution which lowers its energy. Rather, there's very many solutions that lower the energy simultaneously. And this sort of, I don't know, ground state entropy or something requires something interesting. All right. So geometric frustration occurs in a variety of crystalline materials. And a famous example of geometric frustration is the Kagome lattice. So maybe you've learned about antiferromagnetism in the Kagome lattice, but it's pretty easy to understand why antiferromagnets are confused in a Kagome lattice. If you have any nearest interaction. And if I think we energetically want to, okay, well, I can't quite get them to point exactly in opposite directions. I can just, lower the energy. But even so, if I specify the orientation of spins in one triangle I don't know what to do with them. So you can quickly convince yourself that if I look at the and I can have a file and that's very same configuration. Now let's think about the same physics but how it affects now the spin of particle motion. So imagine I have a particle that is in a superposition between three many sites. There's a certain probability amplitude to be at each side of the line. And that probability amplitude is a complex number, so it carries a complex state. Now we'll ask, what is
Excuse me,
energy of
we
this
don't have
particle in the
good
lattice?
sound. We need good sound. Stay close to computer, please.
Okay. This expression I have up here with the cosine. So phases on nearby phases so now let me ask this question: what state maximizes kinetic energy? It would be one where the phases on neighboring lattice sites point in opposite directions. It kind of sounds like what I just told you. So in fact, for the same reason that anti-ferromagnets are frustrated in their orbit, similarly, the orbital states are also frustrated. There is no single highest energy state in the Condensed lattice. There's very many. And you can see that also by the following construction. All right. I think it has to do with whether I'm staring at or not staring at my computer, which is very directional in the sound that it picks up. So I apologize. An area mic I would do better, but I don't. Okay, so I'm going to not worry about it. Great. So we can see also the following construction. Imagine I take a part and I localize it at 6 micrometers. And that part, so that particle is in a superposition of these 6 states with equal weight. And a quick glance at this, you realize that the is stationary, can't evolve. So normally you would worry, well, the particle kind of escape. In this case, it can't. So there's a probability amplitude, let's say that the particle tunnels and leaves the hexagon, but it's canceled out by this probability. And so therefore, this state is stationary, it doesn't evolve, but it's localized. If it's localized, it's a superposition of many different momentum states. And therefore, all those momentum states also have the same energy. All those block states in the lattice have the same energy. Otherwise, this thing would evolve. So corresponding to this localized stationary state in the Condensed lattice, there's a flat band. There's where all this macroscopic number of states lie. There's a flat band in the Condensed lattice. And that's the nature of, that's the consequence of geometric frustration there. Okay. So we've been doing some experiments, first to create a Condensed lattice, and then to start understanding in the orbital sector some physics associated with these flat bands. And that's what I'll try to tell you about with a pertinent. Yeah, right. And we have the s orbitals at each site. There's also a portion. This is not a confining factor. There's also a local minimum. So it could be that that's exactly what that is. But anyhow, when we well, so here's the unit cell of and these are the 3 connected bands that are working. The bottom 2 look kind of like graphene.
Dan, please stay close to the computer. We don't hear you.
Again, that would be like the orbitals from each of these, but it can also be one of our. Oh yeah, sure. And ER is like the recoil energy with this space. Yeah. Okay, so there's a band crossing here. And then there's another band crossing. There's another band. And that has to do with the yeah. Yes, it's the same gamma point. So I should probably profile. Other question? Yes. Yes. Okay. Great. So just a reminder, this is how we construct lattice by experimental setup. So we overlay two triangular lattices, one formed with short wavelength light and the other one formed with long wavelength. And an essential part of this apparatus is that we can independently control the position of each of these two-dimensional lattices. Yesterday, I talked about the fact that we can accelerate the lattices. That's part of our control. But here we can also just change the static relative position of the two lines. And we do that by changing some phases of light beams and then using it to parameter. Okay. And then we end up with this construction. So we overlay two triangles, an intensity pattern shown here, which is a triangular lattice intensity surrounded by some higher intensity. If I just have the green line on, the patterns fall at the right. Here's the triangular lattice, 6 volts has 6 years. And the spacing you see here is. Now, if we overlay it with this lattice is red detuned, so it's about that dark spot and the bright spot. And if I align things properly so that the dark spot of this red lattice overlaps with one of the dark spots of the lattice, then we get this overall lattice potential. So of the sites in the green lattice, site D, and that leads to a. So now at lowest energy, the atoms would be in these 3 equivalent sites, and these form the triangular plexus. And then there's this 4th site, which is energetic, and it's done smoothly. So as we increase the intensity of this lattice, we gradually transform the geometry. Yeah. If we tune it high enough, exactly. So if we tune it so that it's larger than the hopping energy, larger than interaction energies, larger than whatever, then yes, we're in a Kagome lattice. Yeah. Not very much. So that's good. That's a good question. So how flat is this band? So what you find out is the band is flat, save for the deviations from the Kagome lattice. Deviation comes from hopping into this intermediate cycle. That's right. So the strength of that would be 3J. Okay, so it's like J squared divided by the n. In fact, that's the band of this subject. It's a little bit cool. And you can control that by. Okay, so let's use this ability just to do a physics test and see what happens when we take a state of matter system and we convert it from one lattice geometry to another. And you see how I can do so smoothly. I can smoothly tune from a triangular lattice to a Kagome lattice. And as such, I drive a kind of structural change, not structural change in my lattice geometry. So in condensed matter physics, you all know this, there are phase transitions that occur in the electronic sector that tell us, let's say, different transport properties or whatnot of a system. There are also phase transitions that occur in the ion sector, like that a system can undergo a structural phase transition. So an example of that, which I've been told about, is this stuff called vanadium dioxide, which undergoes, it turns out, two transitions simultaneously. So at a particular temperature, it goes from a insulator to a conductive state, from an insulator to a metal, which is something we usually associate with interactions going from being relevant to irrelevant or important to unimportant. But at the same time, because the crystalline arrangement is, after all, dictated by what the electrons are doing, because they're part of the glue that holds the crystal together, it also undergoes a structural phase transition from, I don't know, some crystal to another. And so then you face interesting questions, which make people pay a lot of experimental attention to vanadium dioxide, which is like, what's causing what? Is it the electronic phase transition and maybe a rearrangement of electrons that distorts the crystal? Or is it the distortion of the crystal that makes the electrons do something different? Okay, so in a cold atom setup, we dictate the crystal, and it's not entirely true, but the atoms largely don't change the crystal. So now the two effects are separate. We can separately make the crystal do what go in a transition from one to the other, and it's unaffected by any property of the atoms that are propagating within the crystal. So if you will, it's a chance to kind of disentangle these two effects. Okay, so what will be our test case of this kind of physics? We're working with bosons, so I won't look at the metal to insulator transition. I'll look at a superfluid to insulator transition, which occurs in the Bose-Hubbard model. So the Bose-Hubbard model is a model where bosons are hopping from site to site at nearest neighbor, and they also have an on-site interaction with one another. And what we know about the Bose-Hubbard model is that when the atoms are weakly interacting, when U is small, then the atoms at low temperature form a superfluid. But when the interactions are very strong, the superfluid order is suppressed, and instead the system becomes insulating. It becomes favorable to adopt a state where there's a fixed number of atoms per site, and it costs energy for atoms to go visit their neighbors. So the superfluid order is. And this transition, sorry, what? A little bit of, yeah. Okay. So maybe worth talking about more. All right. Now, if you do like a mean field theory of the superfluid to Bode insulator transition, I'll talk about that in a little bit. You get a prediction for where this phase transition occurs. Let's say at zero temperature, where the transition from superfluid to Bode insulator occurs. And it occurs at a certain value of the interaction strength, which it turns out to be scaled by not just the topping energy, of course, which sets the basic energy scale in the problem, but also by the number of nearest neighbors. That's the prediction from mean field theory. Okay, so now we think about the physics that we have on the table. We have a way of transitioning a system from a triangular lattice, which has a 6-fold coordination, to a Kagome lattice that has a 4-fold coordination. So as my crystal undergoes a transition from one phase to another, it might be that this scaled parameter goes from one side to the other of the phase transition, and therefore the structural change drives also a phase transition in the fluid. All right, so here's and in each And then we and we can look at the velocity. And in the superfluid regime, we end up seeing this accentuated, which we see both at and also the reciprocal lattice. And these are versus if we're in the strongly interacting regime, then those is not how more or less these. But we definitely draw. So if I compare, let's say, these two, right? So we're going to have in the triangular lattice at a particular topic, I have prominent superfluid peaks with better contrast. But in an equivalent Z value U, that is sufficient to drive. Will, by driving a structural transition, I go to that's kind of my point. Always have no. Yes, that's a little bit also, it's also right that we addition to that. The question is like or is it I mean, yeah. We have a plan. So there's a sharp. Let me say there's a sharpish structure. There's a lot of things that not as sharp. But there's experimental. The central peak here, for example, why is it so fat, whereas these ones are pretty narrow? And so they're still not exactly. Okay. So now let's see if I can do anything more. I look at a graph like this, and you're confirming to me that it's kind of hard. Like where exactly?
Top left, bottom left.
This is the triangular ladder. We have repulsion. This,
Going across.
no, I'm moving down. So down is going out of the red lattice, and it's doing the and going sideways is yeah. Okay. So I mean, to some extent, who cares? You know that there's is not always perfectly. But I'm going to like, can I as a precision many bodies point? That would be a nice goal. So you can ask, well, great, how well have you constrained the location? And it turns out we've done a very bad job. So there's been a number of measurements. What was even instance, maybe people would get. But we've been able to constrain the actual transition point at the level of like 10%. And there's various reasons why that's the case, but it has to do with some of the things that you were asking about. It has to do with non-zero temperature. It has to do with like visual. It also has to do with anhalogeneity. Experiments are done with a limited number of atoms inside of a bowl. And so now in this experiment, the local conditions are varying. I might have like a region in the middle, which is like a long insulator, exactly beyond the site. And then next to it, at lower density, I might have, or lower chemical potential, I might have a mod insulator. And between the 2 and the 3, there should be a sliver of superfluid, because that's what the phase diagram is. So in fact, I should never see the superfluid fraction go exactly to the to see its problem. So all these effects make it pretty hard to pin down the trend. So, so what can we say precisely? So we came up with an idea for how we could use our system in spite of finite temperature, in spite of analytic, still to do some precision test of something. And the precision thing we're trying to test is this scaling of U over Zj. Okay, I want to know whether the phase diagram of the Bose-Hubbard model is the same in all crystals, save for the coordination number. That's like a hypothesis, and I want to test it precisely. Okay. In a real system, it applies. Okay, so let me explain how. In mean field theory, rather than what's the state, you ask the simpler. You assume that the state is a mean field state. It is some density matrix at every site, and it's the product of all those densities. And then in that mean field theory, you ask, when does the phase transition occur? And under those conditions, you don't pay attention to the overall geometry of the lattice. The only thing that matters to you is locally, how does this density matrix couple to the density matrices that are nearby? And that's where this scaling with Z, the number. And from this mean field theory, you get a prediction for the, as a function of the chemical potential, the interaction energy, and also the temperature of the system, all scaled by the interaction energy and all scaled by the number of nearest neighbors. You get some prediction, some phase diagram that tells you everything you need to know about it. Tells you what's the density, what's the condensation, and also what's the entropy. Right? Those are kind of 3 thermodynamics that are predicted. Okay. Now, how about in a large system? So now I can think, well, I have this inhomogeneous container full of atoms. Let me try to apply not just mean field theory, but also and get macroscopic properties like the total particle number, the total condensate number, the total entropy by integrating up the local values all at all of the locations. Okay, so these are the expressions, right? It's all an integral over the local mean field properties. And then here there's this other quantity K, which basically summarizes the volume that's occupied by my gas. Okay, so with this prediction of mean theory, we're going to do a precision test. What we're going to do is take a gas that starts off with a fixed atom number and a fixed entropy. Okay, so and the entropy. And we take the gas and we introduce it into one of 2 different geometries of the lattice by sort of adiabatically loading it into the lattice, hopefully while preserving the entropy. And now we can have a very precise test. If you compare the 2 systems, whatever we measure about, but we compare them under the following conditions, that they have the same atom number, the same entropy, the same scaled interaction energy, and the same relevant volume K, then everything about the 2 systems is identical. So for example, if I measure the condensate number, right? The condensate number depends on 4 parameters. The scaled chemical potential at the center of the gas, the scaled interaction energy, scaled temperature, and this quantity K. So it depends on 4 numbers. But if I fixed K to be the same, because and I fixed U over Zj to be the same, because I know how to tune them, and I have the same entropy and I have the same particle number, then the condensate number must be the same in the 2 lattices. Everything. And that's a way in which I can test something about the phase diagram without actually knowing what the temperature is and without requiring it to be homogeneous. I can just basically make a direct test of this scaling hypothesis. Okay, so here's our attempt to do so. We measure the condensate fraction, actually it's the coherent population in these peaks, versus U over ZJ compared for a triangular lattice and a Kagome lattice where we've adjusted K to be the same. And okay, so you see what you often see first graphs on pretty well. And we can also now quantitatively just ask ourselves, well, how tightly constrained is this? How much can I slide one curve past the other and still get it? And what I find is the two curves, their positions on this axis, let's say, should be related by the ratio of nearest neighbors, like a 1.5 scaling of one curve on the horizontal axis versus another. And I find that the data are telling me that that value is not 1.5, but it's 1.6 plus or minus 1. So it's again at the roughly 10% level or a little bit better, but it's, if you will, a precision test of a scaling hypothesis. It's a particular, effort to use a quantum simulator to ask some real question. Yeah. Yeah. Yes. The localization. Because in this band structure, when the gas is very, very cold, it doesn't know about the hot band. But when I add interactions and the particles, of course, can explore the rest, I would expect them to see that there's this sort of barrier of motion and to kind of freeze a little bit earlier. I would expect that the uninsulating frustrated versus the front. So I really thought that the scaling buffer. Okay. Is that the scaling hypothesis out of being succeed? Very simple. Like redoing this. Phase and reading how it. And there's looking. Well, then of course you have this inhomogeneous. Yeah, signature. As you can read it, and you find this is about that's really good. But in spite of you, yeah. And we can I was wondering. Yeah, so for example, yeah. Yeah. Maybe this one we're still part of it. Could it be like how much was it? Because that would be, I think, a view over state that would be more sensitive. Yeah. look deep in the, when your gas is like Bose condensed here at the gamma point, you would think that the only thing matters is the local. That local dispersion, of course, varies D. That's exactly why. Yeah. And deep in the non-insulator regime, you know, you can have particle hole excitations, but they go very far. And so things also become very, very short range. And so all you do. So deep in the insulating, deep in the super fluid limit, it's the scaling to work. And then I would imagine somewhere near the phase transitions it should work really quick. But the system has a lot of atoms near the phase. Don't see. Yeah.
So, like, you just
Not just.
so then
Yeah.
Can you make your lattice?
Yeah.
Because there's a Bose form.
Yeah. Yeah. People have been looking at it, you know. It's a little hard to really, you know, very robust. Yeah. You can add this. Order. So, people. Okay. Oh well, so we don't see any evidence of geometric frustration in the flat band of the experiment, puzzling him. So, okay, so let's see if we can do something even simpler. Can I have anything that measures the dispersion relation and shows me that there's a flat band in the Kagome lattice? And what we decided to do in order to measure this was to try to measure the dispersion relation and see whether indeed. Okay, so I talked about this briefly yesterday, but we have this method for loading atoms into high-lying bands of the lattice. We take a gas of atoms that starts off in the ground state, and then by accelerating either the atoms or the lattice, we've done either, we can push atoms to where their initial velocity is in a particular Brillouin zone. And now if we ramp up the lattice, the atoms end up being mapped directly onto block states of the lattice, and they can be mapped into the different Brillouin zones, that is to say, into the different bands. So, and then we put a force on them. So, and after exerting the force for a while, and then in this case, ramped up stationary, and the atoms then should be. So in particular, we push the atoms and so you see as a function of how fast the atoms are moving below, we should be able to place them either into the first band, momenta between gamma and K, or in the third band. We don't put atoms in this case into the second. So we can put atoms into the third band. And then if we push even further, we can stick the atoms into the fourth and higher. So great. So how well does this work? Well, what we can do is after we've loaded atoms somewhere in band structure, we can examine their velocity distribution. So we just snap off the lattice, the atoms expand, and now I get like a picture of my block state, like you would have gotten if you run a Mathematica program, and it tells you what's the strength of the, what's the population in each momentum state, of your block. So here's Mathematica that tells you how much population you should have in each of these momentum states. And then here's images from the experiment. Okay, so here's where we have attempted to put the atoms at the gamma point. The atoms in velocity space look like when I expect the non-interacting block state. Here's atoms accelerated a little bit. You see there's a very good match between what we calculate the block state should look like from just structure and what the velocity distribution of the atoms are. So if I look at these images, I'm really excited because of method. But I want to do something a little more interesting than that. So what I'm going to do instead is just like instead of comparing these pictures pictorially, I'm going to analyze them. And the thing we're going to analyze in particular is what is the average velocity of this gas? So you see there's this many atoms at this velocity, this many atoms at this velocity, and so forth. So I can just take the average velocity just by looking at this image. And the average velocity turns out to be exactly the group velocity. And the group velocity is the derivative or the gradient of the energy dispersion. Okay, and this turns out to be true both in the single particle limit and also in the interacting case. It's something related to some theorem. And so this is just going to be true of the block state in the presence or absence of interaction. So I can look at this distribution of atoms, I can assess the average velocity, and that is directly measuring the group velocity. And I can plot that as a function of where I've placed the atoms, either in the first band or the third band or the fourth band. What should I expect? Okay, so for atoms in the flat band, this is a fairly flat band. It's not very deep in the Kagame lattice, but anyhow, in the flat band, I expect the group velocity to be 0 because it's flat. The gradient is 0. But if I look at the velocity of atoms in the third band, it's very much not 0. So we measure a group velocity. And puzzled us for a while. But so we had to leave this. And eventually we kind of figured out what was going on. It's an effective help. So if I look at the distribution of atoms in one of these bands, if I take atoms, so let's say this point in the third band of the band structure, somewhere between K and I think N, then you get a certain, you get has some population in the A site, B site. But because we're not at any special symmetry, the population in the A site, B site, C site, and all the atoms repel one another. The overall lattice is not just the Kagame lattice, also lattice generated by their own density, which no longer has the geometry. And so it's this sort of, if you want, renormalization of bands due to interaction that ends up changing the dispersion relation. And we see that as a simply in our mathematical picture that ignores information. Yes, that calculation gives something near that. We have a now you know what you're looking for. So now you put a few more lines. And you ask it to self-consistently figure out what are the block states of the interaction, which is an interesting problem, sort of a nonlinear wave equation looking at its block state. Turns out it's a not very well posed problem. There's actually very many solutions. You have to think about which of them are actually block states. You can end up with more block state solutions than there are than you expect. Well, so it's this kind of stuff. It's a mean field model. Yeah. And that's this top curve, which seems to explain it. All right. So one more message from this effect. It also, but regardless of that, look, I have the ability, as advertised, to put atoms in the third band of the Kagame. Well, that's kind of interesting. I wonder what's the physics of bosons that sit in a flat band. I know that the flat band is at the top of the band structure, but maybe I get lucky and the atoms can remain at the top of that band structure for a long time. and interact with each other and redistribute it within the flat band, what state do they adopt? Do they become superfluid? Probably not. In a flat band, you have like a macroscopic number of states that are all the same energy. Why should the atoms pick a particular state over others? So there's been an interesting discussion about what does happen to ultracold bosons in a flat band. There's predictions about a crystal that forms, which then gives way to a supersolid, which then gives way to a superfluid. There's discussions about fermionization of particles. It's an interesting problem. It certainly would be interesting to study experimentally. But alas, the atoms turn out not to live in the flat band of the Kagome lattice. I might have hoped that they would, because if two atoms are here at the top of the band structure, maybe they can undergo a collision and change their distribution. So two particles collide, and maybe one of them falls to a. But where would the upper particle go? There's a big gap up here, so maybe that would actually dynamically suppress relaxation for a long while. Well, it turns out not to be the case. We find the atoms collapse, unfortunately, the flat band of the Kagome lickety split. So within just a few hundred microseconds, and that's really not enough time for them. So that was disappointing. Lesson is don't work with bosons, work with. Yeah, I mean, maybe what matters is the time up here. So if I do the experiments and I measure within 100 microseconds or something, then everything is. But if I measure longer, then there's time enough for real.
But when you measure, you saw this, so that's where this.
Mm-hmm. Mm-hmm.
But
Yeah, that is not all interaction. I mean, maybe mean field self-interactions, quickly relaxation are some spontaneous emission of longer. I don't know what's free from. Maybe there's somewhat different time scales for relaxing between bands, but unfortunately, it's not very. So we don't have enough time. A lot of it. Yeah. It's not. Yeah, interesting. Split off. Well, often when you split off, but yeah, we've thought about that. Whether we can sort of static now. I don't know. It's not something we're playing with. Instead, with the last couple of minutes, we work with the honeycomb lattice. Okay. So it turns out, and I mentioned this yesterday, honeycomb lattice also has bands that become flat. They're not the s orbital bands; they're the p orbital. And they're a little bit different. They're still connected to bands. And they're protected from below 5 anchors rather than from the. Maybe that gives us more stability. We know how to put atoms into the third band anyway. Of the honeycomb. All right, so why does the honeycomb lattice have a flat band? Okay, so now we're talking about atoms that are in the p orbitals of these sites. Site A and B of the graphene lattice. And in each of them, the atoms can, let's say, rattle in this direction, that's one p orbital, and they can rattle in the other direction. And in these two directions, there's a different hopping strength, as you might imagine. So if I think about two sites, a bond between them, a p orbital that sits in this site and has this orientation, px, has a certain probability to hop over to the neighbor. So I'd call that pi hopping molecule. In contrast, an atom that is rattling in this direction is in a p orbital oriented in the y direction, has a different tunnel strength. We very strongly with the neighbor. A different tunnel strength for hopping, call that pi. And as the lattice is deepened, that the barriers are grown between the lattice sites, it turns out that this pi hopping is suppressed very much quicker than the sigma. So you can get into a regime where only sigma hopping. You also have flat bands in the honeycomb lattice. So here's the dispersion relation, but that's not as interesting maybe as this diagram. So here's a picture of the localized Wannier state corresponding to this flat band. Again, we have a particle that's in a superposition of 6 sites. And this superposition turns out to be stationary and can't leak out of its initial localization. So why is that? So over here, let's say look at site 1. So I have a particle that's rattling, and it can't, let's say, undergo pi hopping because that's suppressed. So that particle can't on its own leave. But it's possible, for example, for the particle, for the wave function here at site 2, to hop over so that it's oriented in the sigma direction and then to leave. But we arrange things so that the probability of this particle hopping into the y-oriented p orbital is canceled out by this probability. So again, there's destructive interference, and this state also is localized. In fact, if you're paying attention, there's 2 different maybe chiralities or something on this street, where I can, let's say, flip the signs of these 3 sites. And that corresponds to the top and bottom bands, which both become. Okay, so similarly, the honeycomb lattice also has a kind of geometric frustration in it, and it has, therefore, flat bands and localized states. All right, so we put atoms into the into the p orbit. We load them into the third band. We actually then move them back. It turns out the moving. So that's a longer loop. Load the atoms into the third band. We have the lattice be stationary. We just see what happens. So here's like a distribution. This is a band mapping image where we piggyback down the lattice and then atoms. This is a direct velocity image of the atoms. You see there's a lot of stuff happening. And let's try to analyze some of this stuff. So let me look at this image right here and separate populations of atoms. So there's some populations that live here at corners of the Brillouin zone. Okay, that's the equivalent of the gamma point, but in the third band. So I can think of the populations there as maybe just being the initial coherent superfluid that lives at the gamma point, but it's hard for me to tell exactly which band it is. And then you see there's population that adds up and eventually fills in the third Brillouin zone, but in kind of a mushy manner. So there's some kind of incoherent population that fills the third band. And then I can also see how many atoms are in the second band and how many atoms are in the first band from this. So I can put it all on a graph. So this is the population of atoms that remain in these coherent peaks. This is the population of atoms, the total population of atoms in the third band, and it remains pretty high for a number of milliseconds. In fact, if we zoom out, it remains high for even 100 milliseconds. So the population in this p band, which is protected from below by a band gap, seems to actually be fairly long-lived. The atoms are rattling around at each of these sites in p orbitals, and something is preventing them from relaxing to s orbitals for whatever reason. So we've started doing some experiments. We do experiments on ultracold and look today. So far, the data from boson black p-band going away from that deep limit where it's not. And we see under those conditions, we see evolution, right? And this is maybe a little bit of detail, but I can see in these images from the gamma to the K point, where the energy is a little bit lower. And I can isolate the population at the K and K points that is full. So from the size, we can measure this. But it's not yet super. So we're seeing the initial kind of a 30 p orbital, and it'll be interesting whether we can see thermalization, so something like a equilibrium phase that forms, but in a situation where we iron out the dispersion and where interactions between atoms maybe make something interesting happen. Okay, so that's roughly as much as I wanted to tell you. I think we'll be back to this experiment. We don't have. You might ask me questions about this quantum computing few minutes or something, but I'll just point out that it's sort of folks that are mostly in California, but also elsewhere. It's a kind of a new institute, a new departments. To me, it's really rich intellectual. AMO physics case and start interacting with people and across different campuses. We're finding really productive connections with engineers that devote themselves to use in our AMO labs. It's been really interesting for me to connect with theoretical computer scientists who are talking to me about the algorithm and computational complexity of things like physics simulation. So this has all been a pretty interesting one. But let me just stop here and if there's more questions, take them. And yeah, sorry to whoever's on Zoom. I think. Yeah. 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 You know, distortion and but just that's then yeah. That being said, I don't want to keep it and be much more and to go along with that. We don't want to we can't have
I have a question about just the last slide that you showed us. So people visit another thoughts.
Yeah, so please run it a moment.
So,
Which data?
but it's- and so, what is it?
Yeah, as a band, it's a little bit pretty. This is there's a lot. Right.
So
Yeah, I'm just.
That just lattice.
Yeah. 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 Cool. And that's cool.
But if you had to estimate. No longer under nail. Sorry, one.
We can actually, maybe. And I know what. From my.
Well, sure.
What did it prove? From that, I know that.
Yeah.
Yeah, so I don't know, I think we determined that it's like. I mean, it's not. All right, well, thanks, everybody.